Thank you for coming. So I believe today's audience is not that much in robotics, but I will talk about how to scale robots. So first of all, I will start who I am. I'm a lecturer at Bournemouth University, and in particular, I'm interested in scaling distributed systems, right? Reliably, so they keep scaling and they keep performing, and if something goes wrong, still there is a really good performance. So I'm not a roboticist, just to state that from the beginning. For me, the interest in robots is that these are machines with lots of interesting capabilities from distributed systems perspective, so that's what I'm interested in. So today I will be talking about various small parts of research that I did with colleagues from Glasgow universities and students. So the reason I worked there for quite a while, so I have very good connections with them, and we sort of keep collaborating. So these are some of the pictures, those I could find. So I will start with simple and basic things, just to make sure that we all, on the same level, we understand what I'm talking about. So robot. So English Oxford Dictionary says it's robot is a machine capable of carrying out a complex series of actions automatically. But the next question, how actually intelligent and autonomous a machine should be to actually qualify for a robot? Is a washing machine a robot? Right? That's the question. So the thing is that robot should sense and act. So we can call it thinking, but it's actually sensing something and then acting on those senses. So that's the answer. And washing machine, if you have one that actually senses that you've got quite a load of clothes that need to be washed, and then collects either around the house or just put it up itself, then you have a robot. Otherwise, I'm afraid it's just a washing machine. Right, let's talk about different types of robots. So when we talk about robots, actually, there's a huge variety of those. So first of all, we have traditional robots. And these are the robots that are in industry and manufacturing for many years now. And the thing about these robots, they are highly automated, right? They're very precise, they're very efficient in what they do. But they're also, most of the time, they're caged. And humans are not allowed anywhere nearby to those machines because they're not safe. So the next thing is collaborative robotics. And collaborative robotics, the aim is to support human. So whatever human does, the machine supports them, so a human can work in a very close proximity to those robots, and we don't need to sort of cage them or take them away. So my interest is actually in cooperative robotics. The difference is that, again, we have robots that communicate with humans, with other machines, with other robots. But the point is on the task, right? They have a task, they need to complete that task, and they do that cooperatively, all together. So they're quite exciting in terms of these are distributed systems, but these are not our classical distributed systems. And the reason is that now we have power restrictions, right? So we don't have just electricity all the time coming in and feeding our machines anymore. We need to consider those things. Wireless connection should be in place, so we don't have this, I would say, reliability and reliance of wired connection. Then we also have quite limited power resources. That's another thing. And finally, each robot is a network of different devices already. So each robot, it's not just a machine or a server or something. It's actually a network of quite heterogeneous devices working together. Another interesting thing about cooperative robotics, that it's not a swarm, right? So very often, cooperative robotics is confused with a swarm, and people use swarm quite a lot. It's actually not a swarm, it's a pack of robots. And the difference is, in swarm we have these small devices, and they're usually very primitive. So what they can do, they can move left, they can move right, and move around, maybe flash. But these actions are really primitive. And when we get these exciting, interesting things, and when the swarm starts to work together, that's when the behavior comes. We have emergent behavior. In cooperative robotics, we may have emergent behavior. It may come out, but it's not the main thing. Actually, in cooperative robotics, each robot in itself, it's sort of not a person, but individual thing that can do quite a lot in itself, but when they're working together, they can achieve even more. So that's the difference. So we talked about hardware that we're considering. Now let's talk about the software part. And actually, there is quite a lot of middleware out there that works with, you can use for your robots, quite a lot. So today I will be mostly talking about ROS, Robot Operating System. Who's familiar with that? Just to get an idea. Right. So I'll introduce ROS a little bit. So the reason we picked it is that that is the most popular robot operating system in the world. Right? There are quite a number of countries using it, and it's a collection of library, drivers, and everything. So the idea of the ROS is that you take it, you install it, and you start using it. And the reason they came up with the idea is that they realized that with the variety of robots, with the issues, complexities that they face, no single lab, not even single university or institute that works a lot on robotics can solve that problem. So they said, let's come together, let's create ROS, and let's all openly source contribute to it. So that's ROS. And it actually exists from 2007. It's a collection of tools, library, and conventions. And there is a now new version, is ROS 2. I'll talk a little bit about it. So what is ROS? ROS is open source, and it's modular. So we can have, we have like a single machine. So we can have a robot just on a single machine, or we can have a collection of robots. And then we have ROS nodes, right, software nodes. And those nodes cooperate, communicate with each other through publishing subscription. And they also have a master node that usually sits outside of the system, sometimes inside, and that one is used for registration. So if you want two nodes to talk to each other, you need both of those nodes be registered with the master node. The communication won't go through the master node. They will be communicating directly with each other, but communication won't happen if one of the nodes is not registered with the master. So that's the design. The thing about ROS is that if you start talking to roboticists, well, depends on where they work. Some say that ROS is just fantastic and works beautifully, but those people who try to have a little bit more complex robots, they all say ROS doesn't scale, ROS fault tolerance is just appalling. But that is all just sort of folklore. People say that, but there is no much sort of evidence for that. And these are some sort of characteristics that you can make conclusions about scalability of ROS. So first of all, we have master node, right? Single point of failure immediately. So we need to register everything, and if it's not a connection or something happens with the registration, we need to restore that, and by the time ROS master node realizes that, lots of time passes. Another thing is what happens if ROS node fails altogether. That's another problem. Fault tolerance. ROS wasn't designed for fault tolerance, right? So ROS wasn't designed for scalability, and ROS wasn't designed for fault tolerance. That's the thing, right? So people say it doesn't work. Well, the reason it doesn't work because it wasn't designed for it. And there are some sort of hacks that is called ROS launch that is sort of provides some reliability and these kind of things. So then the question comes, so how scalable is ROS? So what we did with a couple of students we decided to run a couple of experiments to see how scalable was. And what we did, we started with a single robot, and to run the experiments, we just used the laptop, right? So we installed Linux, we installed ROS, and we started with a really simple experiment. 2 nodes start communicating with each other, and just to see what's going on there. And we look at latency and throughput. We looked at a number of characteristics. So one of them, so these are characteristics of the system. If any of you is interested, so it's a typical laptop, Linux. Then we have different kernel, Python, sort of. If anybody wants to repeat those experiments, the results are here. And the first actually lesson we learned here is that when we work at small scale, it actually doesn't matter whether we use Python or C. So Python, of course, is much simpler. You can do lots of things much quicker there. And C, the idea is that you usually do something hack very quickly with Python and then do some serious work with C just to improve performance. But actually, I'll show it in the next one. If you work on a small scale, then it doesn't matter. And it's actually better to use Python on a small scale and get all your results just the same. And then when you start scaling, then when you switch to C. Right? So just to understand the picture. So we have the throughput over here, and it's bytes per second. And the higher, the better. And here we have message sizes. So we start with 4 kilobyte, 8 kilobyte, 16, and so on. So it's exponential sort of increase. And then we have left, we have Python, right? We have C, right? And then we start increasing the size of the messages. And actually, we start seeing the difference only when the messages are around 16 kilobyte. So if your messages are smaller, just don't bother with the language. Go with Python and then see the rest later. But that's a single one, right? And we need multiple robots, especially it's the distributed systems and it's robotics, so it should be more robots than that. So we came up, we've got more students interested in that, so we ran more experiments. And these are my robots. Exciting, I love them. I have 10 of those. I'd love to have 500, but it's gets a little bit expensive, so I have only 10. And they're really cheap. So if you're interested in having this side project, toy project at home, these are really good. They cost the whole thing with the root, not maybe with the router, but the whole like Raspberry Pi in it and batteries and everything in it. Each robot will cost around 250 pounds, right? Euros, almost the same. So yeah, really good ones. So we did the experiments. And the next thing we learned is actually when you work with robots, start really simple. Like the simpler, it can't go in any simpler, right? And we learned this lesson quite hard way. So first thing we said, okay, we need to design this experiment and we want a demo. And we want robots just following each other. We saw a YouTube video of that, when they just follow each other like a family of ducks or chicken or something like that. And we started developing it. And development was going fine, but when we were running experiments, there were really funny things going on that we couldn't understand what's going on. So we had this line of robots, we couldn't understand, we reduced them to 2. We couldn't understand, we decided to change the whole thing, just exchanging messages. We couldn't understand that either. We ripped that, we just had Raspberry Pi. So in the end, what we had, 2 Raspberry Pis, wired connection, one ROS node on each, sending messages. And only that we understood what's going on there, right? There was an error, we figured that out, and from there we started scaling. But the thing is, in robotics, there are so many things that can go wrong. So my sincere advice to you, if you decide to go for robotics, it's really simple, something that you really, really understand there. So coming back to scalability, so that was the first experiment that we ran. And then when we were figured out the different factors, like, for example, impact of Wi-Fi, how much it changes scalability, impact of going from just bare Raspberry Pi to a robot one, so all sorts of things. In the end, we had these two robots sitting to each other, talking via Wi-Fi, and then we had a number of ROS nodes on each talking to each other pairwise. To make our experiments a little bit more sort of reliable, trustworthy, we changed exchange messages from just simple hello messages. We changed them to actually representative data. So MIT, they collected data in 2011 and 12, and it was sensor data and video data, right? And we sort of fed them to our robots as if we had those sensor and video data, coming through from sensors and things like that. So just to make to understand something. And what we discovered, and it was really exciting, there is a communication volume. I'll explain what it is. So first of all, the name is communication scaling limit volume. We're not particularly good at naming, so this is just what we observed, and we just called it that way. Probably later we'll come to a better solution. But what actually it says that the volume is constant, right? And it depends on number of nodes, it depends on the frequency that you send messages, and then it decides on the size of the message, right? So you have your robots, and they're communicating with each other. And the thing is that for your system, for this particular system that you have, you'll always have volume to be constant. And then if you want to have a best performance for this particular number of robots, then you need to figure out sort of number of nodes. Well, it's sort of given, right, with your system. But then what you can sort of play with is frequency and size of messages, right? Find out the balance. And then if you start increasing the frequency, then your message size should go down and so on. So there is a dependency. That was really exciting to see. But this experiment was just with two nodes. And what we have here, we have message latency, and then just every message, we just show how long it took, right? And when we talk about latency, the lower the better. And what we see for this particular sort of set, two robots, it's actually just four nodes, right? So 2 robots, 2 nodes each, and they just start communicating with each other. That's sort of the best. That's the volume that it can handle. If we start increasing the number of nodes, then we should decrease the frequency, we should decrease the size of the messages. So, but that was just for 2 nodes, and the question is, okay, we found it for 2 robots. Will it hold if we have a larger number of robots? And actually, it will. So there may be more factors, but for 4 robots talking to each other, there is still this volume there, and there are no other sort of noises that impact the volume. So it still holds at 4, and we're confident that it holds for larger, just need some more experiments to find. Another thing that we sort of realized that middleware makes a lot of different. Operating system makes lots of different. So the assumption is, okay, we have Linux, we have ROS, and then it just goes improving, and then doesn't matter which one we install, just work for it, and the main thing is how we configure. But actually, the version of operating system, the version of middleware varies a lot. So our students ran experiments with ROS Kinetic, and that was Ubuntu Xenal 32-bit. And then we had ROS Melodic and different Ubuntu Bionic 64-bits. And the performance is really different. So here we have latencies. And with latencies in milliseconds, the lower the better. And then we have message ID, so how long it took each message to get delivered on different frequencies, so different colors at different frequencies at which messages are delivered. So if you can see there, for ROS Kinetic, it goes up to 500 milliseconds, whereas for ROS Melodic, it goes only up to some 35 milliseconds. So the difference is dramatic, right? So if you decide to go for something, sort of advice and lesson that we learned is pick your key characteristics that you really care about and then run some simple experiments, some simple benchmarks to see how different operating systems, different middleware will perform those, and then go for the one that works better for your particular case. Another one was ROS2 has significantly, that's another sort of lesson that we learned about ROS2. Because the thing is that ROS, there's there, but then we have ROS2. People say that ROS2 is better, but then there is a resistance to start using ROS2. So whether there is a difference. So we decided to run experiments and see whether there is a difference. Well, there is. Right? So we took ROS melodic, the one that was performing better, and we compared it with ROS2 crystal clemis, and in this time, both operating systems are the same. So, and here the scale is the same, just easier to compare, up to 25 milliseconds, and we again have latency. The lower, the better. And if we look at ROS2, then it goes within some, usually between 2 and 5 milliseconds with different frequencies, whereas message latency in ROS, it's much spread and everything. So the difference is that ROS2 was, so what they did there, they first of all removed the master node, with which you need to sort of talk to register your nodes. And the second thing is they changed the communication channel. Right? So it was designed to handle more messages. When we talk about fault tolerance, so ROS2 handles better fault tolerance in terms of that if a connection fails or something fails, that it keeps working. An interesting thing about fault tolerance that we discovered is that actually in robotics and roboticists understand fault tolerance absolutely different. Right? And was quite interesting for us. Because in distributed system, fault tolerance means what? The system fails, and fault tolerance means that it comes back automatically without human intervention and keeps working, right? So you sort of restart your system automatically. In robotics, fault tolerance means that if your system, something fails, then your system keeps working without those components. Right? So that's fault tolerance. So it's interesting to speaking to other sort of disciplines and realizing that the terms that are so natural for us, so sort of obvious, actually they understand completely differently. Right. So that's the sort of take on fault tolerance, that it failed. We are not trying to restart it. The only way to restart it manually, but fault tolerant, that is, keeps working. And that's a sort of another lesson, not a lesson, but a discovery, I would say, discovery we made, is that non-defensive programming improves fault tolerance, right? And it does seem a little bit strange, and it doesn't sound controversial, but I explain what it means. So we did some experiments with, again, almost the same people. So Erlang, I almost never give a talk without mentioning Erlang in any way. So who's familiar with Erlang, just to get an idea? Fantastic, great. So Erlang, it's a really lovely and nice language. It's a really industrial flavored language. It was invented at Ericsson. It's not particularly young, from 1986. And it was specifically designed for fault tolerance, scalability, massive concurrency, and soft real-time. So when we talk about robotics, usually we talk about hard real-time, right? But actually, ROS also doesn't provide hard real-time guarantees. It also provides soft real-time guarantees. So those things about hard real-time guarantees, they all work around. So Erlang sort of complies there. So what it is, non-defensive programming approach, it comes with two philosophies. The first philosophy is share nothing, and the second philosophy, let it crash. And when we talk about human safety, then it does sound a little bit funny, right? Just let it crash. But in reality, it's not just let it crash. It's also quite a number of supporting mechanisms that enable let it crash work effectively. So what is that? So first of all, share nothing, it's each process has a private state, right? So they're called actors, and actors are compared a little bit like humans, right? In that respect, that, for example, if I don't like somebody's lever, for example, it's not just I put my hand, change something there, and let the person go with a different lever, right? So if I don't, I'm a doctor, assume, and I see that something is wrong, the only thing I can do is tell that person, look, something is wrong with your lever, right? And in this case, there is no like operation or something like that. It's more like take a healthier lifestyle and things like that. So each state has a private, each process has a private state, and nobody can change the state apart from that same process, right? And if messages, other actors wants to change that process, they need to send a message, right? So that's how they work. Actors send messages to each other. It does a bit complicate life, but the point is that if any of those processes fail, it won't impact any other process, right? Any of the actor just went down, and that's it. Oh well, that's life, right? But and here it goes with let it crash. So the attitude is, if we see that the process start behaving in a funny way, rather than keeping it alive and supporting it somehow and making sure that it's keep going and somehow, what we do is just kill that process and restart it again, right? And to do that, we have supervision trees. So processes supervise each other, they monitor each other, and what they do is they look at a number of processes, and one of them failed, they restart it. Then it failed again, restart it. And then there are different behaviors. So when, for example, it failed 10 times, it says, okay, something is going wrong there. So what we do, we kill the all processes that we supervise, kill the process itself, and say, okay, supervisor, do something. And it's really good, because what we can do if processes keep failing, we can just remove everything from that particular server, from that particular machine, move implementation somewhere else, and let heal or fix that particular machine. So another thing is lightweight processes. So of course, if we have really heavy processes, it doesn't matter how long, how much supervision we take. It will take time to kill the process. It will take time to restart the process. So the idea is that processes are really light, and it's really simple just to kill them and start a new one. And then registered names. Registered names, it's something like synchronization. So, for example, there is a process, and every node, every machine, every process in the system know that, for example, that particular process is called organizer, for example, right? And then if organizer fails and is restarted, then nobody needs to know its ID, because of course ID changed, but the name organizer is the same, so other processes, other actors can keep communicating on that process. So that's Erlang. Erlang is actually quite widely used, so it's not that it's not used anywhere, nobody knows about it. It's actually quite efficient, and I think the flagship sort of thing about it is WhatsApp. When it was handling half a billion, monthly users, they had around 35 developers who were working with that, and were able to support that. So the language is really efficient for its particular. I'm not saying that Erlang is a silver bullet and everything should be implemented on it, but the areas where it's good, it's perfect, right? And yeah, it really works quite well. So majority of it is messaging, any kind of messaging. So I think Sixer said that actually 95, maybe more, % of world internet traffic goes through Erlang, just because routers use Erlang, and then NoSQL databases, but 335 was it? Games, if anybody, Call of Duty, the server side is written in Erlang, so it's quite a big one. So the experiment that we did is, I remind you what we're talking about. We're talking about using non-defensive approach to scale and to enable fault tolerance in robotics, right? So what we did face recognition, and for that we used a laptop camera, so that's a robot. And we implemented two systems, right? So ROS, as it is, with its hacked sort of fault tolerance, whichever exists, and then we used Erlang. So the only difference we did, we just changed the supervision thing. So the raw system, the drivers, everything, it was there. And the results were really amazing. So what we have here, we recorded 100 messages, right? And then we were playing them again and again and again. And the idea is that, so there are two implementations, one in ROS, one in Erlang. And we have a quality index, so the higher the better. But it obviously doesn't go beyond 1, so 100% is the best one. And then we start sort of playing our messages. So we have frames, so each frame has its own. And we don't care whether it goes up and down, but the point is that actually they should concur, right? So we have a green one, and that is the sort of ground truth. So these are how the recognition goes on. Then we have blue one, and it's sort of soft kill, right? We send a request, we say, please terminate, and the process terminates. And then we have brutal kill, and this is where just terminate and the system behaves somehow. And then we have the same thing for Erlang, right? And what we did, at some point, we started killing the processes. And then here we show the percentage, right? So here we killed 10% of processes, of all processes that were there. And the way it behaved is it started sort of deteriorating. And then eventually it was like, no, I'm not coping without these processes. The system just died. And in Erlang, we killed 50% of all processes. And the system sort of deteriorated for some time, but then it goes back to life. So what we realized, so we not with this seemingly funny approach of let it crash, we didn't just reduce the downtime, but we actually mitigated negative impact of the failures altogether. So that was really, really nice finding. I went really quickly today. I expected to talk about 50 minutes, but I'll let you have a chat a bit earlier today. So these are the lessons. I just put them all together. These are the lessons that we learned from all these small projects, starting with languages, different operating systems, volume, middleware, and then non-defensive programming. So thank you very much.
Thank you, Natalia. Well, since we have another 26 minutes or so, if there are any questions or comments, we certainly have time. Yeah, go ahead. Just loud.
About this volume you were speaking about, maximum level, is this somehow related to the physical bandwidth of the network, or is it something that is still way below the physical bandwidth of the network, the underlying network, and it's more inherent to point-to-point communication with many partners?
Yes, that's a really good question, because everybody heard it.
Could you repeat the question?
Right, what impacts the volume? Is it just a low-level network, or there is something else? So we believe that it's very much about hardware, right? So first of all, we have Raspberry Pis there, right? So I suppose if we change it to something like GRISP card, with a much, more sophisticated hardware that will be better. But I think it's also software that is serves there. So of course, mechanisms that implemented at Ubuntu level, subscription, and PubSub mechanism implemented at ROS. So all those sort of mechanisms come in play. So that's the thing. So there is no such thing, we believe at least, there is no such thing as communication level, a communication volume that is sort of recalculated and we can bring to another system. It should be calculated for every network. So if we replace the operating system, or we replace the ROS, or we replace any bit of hardware, I think we need to recalculate that again. But that's a really nice question. I suppose we can just go and measure it. Yeah, thank you.
Another question. Well then, thank you.
Yeah, thanks a lot.